we're Team 28 of the EML 4806 Robot Modeling class for FIU, Fall 2015. We'll be presenting our Project 1 on mechanisms. The team consists of Jesse Fontus, Guerrero, and myself. For this project, there are two parts. Our team specifically got analysis of the slider crank mechanism and analysis of the four-bar system. For the slider crank, we'll have to do position analysis, velocity analysis, and acceleration analysis. We'll also have to find a realistic application of the mechanism. For synthesis, we're given specific parameters for a four-bar system. We'll have to synthesize a system that will behave in real life and behave realistically. We'll also have to find a realistic application for the mechanism. Now, mechanisms aren't anything new. We've made advancements in with modern technology. However, you can find examples of mechanisms dating back to 3000 BC. Now, here's a few examples of early mechanisms. On the top is a wooden bird that can fly, created by architects of Tarentum in 3000 BC. On the bottom, we have Thomas Edison, who created a wooden dog that could talk. Now, originally, robotics was a field that was solely mechanical engineering because we haven't invented electricity or computers yet. However, with advancements in recent technology, we've introduced electrical engineering, computer engineering, and software engineering in robotics. So we have AI systems and robotics like so. Now we have Guerrero with part 1 of our team project.
Thank you. So our problem statement for part 1, we are given R1 as our input, and we have our theta 2 and theta 3 as our unknown values. We have determined our R2, theta 1, theta 4, and theta 5 with educated guess, and our known parameters are theta 3, theta 4, R1 prime, R double prime of 1, and the distance of QS. So to find the position analysis, first we have our position equations. With those we can find the scalar equations, and the scalar equations may be squared and added, so theta 3 can be eliminated, so theta 2 is the only unknown. After, this equation can be reduced all the way down to a quadratic equation where this value t is represented as tangent theta 2 over 2. And this results in giving us two different theta 2 values for position 1 and position 2. These theta 2 values can be plugged into the equation above to find the two position equations for theta 3. Now, resulting in our input R1 to be 31 to 45 inches. And here we have an example when R1 is 36, 37, and 36 inches. We have our R2 values, our theta 2 values, and our theta 3 values. Now for velocity, for the S-point trajectory analysis, we have used the following two equations to find our position for x. We have been given that the QS value, the QS length is R2 over 2. Now that we have found the parameters, we can now calculate velocity. We can calculate velocity using the matrix above, and we can find our theta 2 prime and our theta 3 prime. With these values, we can use the following equations to find our R prime of Q and our P of, our P prime, which gives us the velocity of point P and point Q. Then we can find the acceleration of point P and point Q using the matrix above to first find our acceleration at 2 and acceleration at 3. Using the acceleration, we can plug it into the following formulas to figure out what is the exact acceleration at point Q and at point P. Here is our slider crank mechanism in the animation. And here are some real life applications. Slider cranks can be found in as a piston combustion engine and as in a backhoes and even in a ping pong table, as shown. Thank you, and Jesse is going to talk about part 2. Thank you.
Hello, my name is Jesse. I'm going to be talking about part 2, which is the synthesis of a 4-bar mechanism. First, here are the knowns we were given. We were given the position 1, which is A1, B1, also position 2, and position 3. The unknown values are the R1, R2, R3, and R4, but we must find the A knots and B knots in order to find these equations. So in the next slide, we'll see how our calculations are done. Here we see the matrix C's that are used to get the A naught values and B naught values. As you can see, we use all the A1, A2, and A3 values in inverse matrix, multiplied by, once again, the A1, A2, and A3 values to get our A naught. Also, same for the B naught. We use the B1, B2, and B3 values to get the B naught and X and B naught Y. Once these knot equations are found, we are then able to find the distances with a distance equation. And we see R1, R2, R3, R4 are found. And also, after these are found, we are then able to verify that this 4-bar linkage complies with Garchoff's rule, which is the longest and shortest link is less than the other 2 links. And with that application, we're able to identify the linkage as type 1. Also, it was a double crank, which meant the large and small links rotate in full 360 degrees. Here you see an example of our 4-bar mechanism and how the largest and shortest sides rotate 360 degrees. Here also, we're given the task of making sure that at each position that the mechanism goes through each position in a row. And through Excel, we're able to do iterations. As you can see, P1, which was A1 to B1, and these are the 2 A naught and B naught points. And as you can see, position 1, it was able to go to that position. Here's position 2. Also go to that position, and also position 3. So with these 3, we're able to prove that the points went through each position. And lastly, we're given the task of seeing real life scenarios of these situations. First scenario was a locking plier, which is made up of a rigid link members connected by joints. And as you can see, the joints right here, A, B, C, and D, all connect to make a 4-bar mechanism. And also the closing door, the mechanism here, as you can see, used on a door to open and close the system. And in conclusion, we were able to use Garchoff's law to the 4-bar synthesis to determine that it was a type 1 mechanism. We're also able to verify that all the links pass with each position. And also for the slider crank analysis, we were able to solve for the unknown values through position analysis, velocity analysis, and acceleration analysis. Also, we were able to find the trajectory of the S point. And for both of these, we're able to find real-life scenarios for the situations. So that concludes our project, and thank you for listening.